Hi everybody, welcome back. In this video, we will discuss the integrated rate law. So the integrated rate law allows us to see the dependence of concentration as a function of time. And we will focus mainly on first order, second order, and zero order kinetics. But remember, there are other types of kinetics out there, just focusing on these three main scenarios here. So let's derive the integrated rate law for first order kinetics. So we're going to start with the generic reaction. Reactant A produces products. And we learned in the last video that the rate law for a first order reaction looks like this, where rate is equal to the rate constant K times the concentration of the reactant to that order. And when it's first order, we generally do not write the 1 up here. We just assume that if you see it written as such, then that's first order with respect to the reactant. Remember, the rate law allows us to see how the concentration of the reactants affects the rate of reaction. In addition, in a couple of videos before this one, we learned about reaction rates. And if we wanted to write the reaction rate as a function of A, we would have written as the change in concentration of A. Remember, if A is a reactant, it's decreasing over the change in time. And we always divide by the stoichiometric coefficient, but we're assuming for this reaction it's just 1. And so that reaction rate here was also equal to the rate of reaction. It was just a different way, and we could measure the concentration of A over time and figure out the rate of reaction. And then when we discussed the rate law in the previous video, it was allowing us to see the rate of reaction as a function of just the concentration of the reactants to a certain order, right? So we looked at 0, first and second order. In this case, we're looking at first order. So I'm going to set the reaction rate equal to the rate law because they're both equal to the rate of reaction. So I'm going to say that this is equal to K times the concentration of A to the first order. And like I say, just remember that we learned about the rate law in the previous video. And also in previous videos, I discussed reaction rates. And so in this case, reaction rate, if we're talking about A, would be the change in concentration of A over time. It's negative because A is a reactant, so it's decreasing. And so I'm just setting these two equal to one another. And this is referred to as the differential rate law. Now, from the differential rate law, we will integrate. And since the prerequisite to my class is only college level algebra and not calculus, I'm not going to actually do the integration. I'm just going to show you the final answer after integrating the differential rate law. So what we get from here is the natural log of the concentration of A at a specific point in time, so T for time, is equal to the negative K, the rate constant T, plus the natural log of the concentration of A initially at time is equal to 0. And so I just wanted to reiterate that the concentration of A, when you see that little 0 down there, just stands for the initial concentration. And so we've discussed, if you remember our conversation about Clausius-Clapeyron, that specific equation allowed us to have an equation of the line, right? In the relationship of vapor pressure and temperature. It's the same thing for kinetics here. You will see that this equation is an equation of a line. And what's really important from that to make note of is that the slope of the line, when we plot the data, in this case here, is negative k. And we can see that in this figure below. This is first order kinetics. In addition, something else to make note of is that y is natural log of the concentration of A at a specific point in time. So if you were given data, and remember that all kinetics has to be experimental, so it's going to be a lot of data analysis. The way that I remember to plot the data, and if I know I have first order kinetics, then I look at the equation for first order kinetics and I see that, y, I need to plot natural log of A as a function of time, so for the y-axis. And then I look at x here, and I see that x is just time, okay? And that should be plotted on the x-axis. And if I get a nice straight line with a negative slope, then yes, I do have first order of kinetics. If I don't get a straight line, if it's some sort of, curvy line, then it's not fitting the true first order kinetics. Now, another way that we represent the first order kinetics equations, it's still the same equation, but just rearranged, is we write it as natural log of the concentration of A at a specific point in time over the natural log of the initial concentration of A is equal to negative KT. And so this is the same equation here as we see right here. It's just rearranged. And you're going to see how that's useful when we discuss half-life in the next video. Okay, this will be nice to have as a ratio. All right, so let's move on our investigation of kinetics and look at second order kinetics. So I'm going to do a very similar approach. I'm going to assume that I have reactant A here to produce some products. And we learned in the previous video that if we wanted to write the rate law, then rate is equal to the rate constant times A, and if it's second order kinetics, then the superscript is 2 up top. Now the reaction rate is still the concentration of A as it's decreasing over time, but now we set it equal to the rate law, Ka to the second, right? So this is still the reaction rate for this reaction, but now that we understand this is second order kinetics, we set these equal to one another, and so we see that second order kinetics there. Remember that this is just the differential rate law, but we're really interested more so in the integrated rate law because it gives us an equation of a line. Anytime we have an equation of a line, this makes our life really easy. We can do linear regression analysis and get so much information from that line. And so the integrated rate law for second order kinetics is 1 over the concentration of A at a specific point in time is equal to KT plus 1 over the initial concentration of A. And as always, I always write y is equal to mx plus b because that allows me to identify the important variables I'm looking at here. Slope is a big one here. The slope of second order kinetics reaction mechanism is just k. And it has a positive slope. So this second order kinetics looks different than first order kinetics, which had a negative slope. I also see with my y-axis that I would need to plot 1 over the concentration of AT, as you see here. And then for my x-axis, I would need to plot time. So if you have second order kinetics, you're always going to want to plot 1 over the concentration of AT versus time. And if you get a line with a positive slope, then you know you have second order kinetics. If you get a curvy line, it doesn't fit the linear regression analysis, then second order kinetics is not taking place. And then finally, zero order kinetics. We see here that we're assuming A goes to products, but the rate law for zero order kinetics looks like this. Rate is equal to K times the concentration of A to the 0 power. Now anything to the 0 power is equal to what? Good, it's equal to 1, right? So effectively, the rate law for zero order kinetics is just equal to K. So if we set that to the reaction rate, the concentration of A over in change in time is equal to K. This is your differential rate law for zero order kinetics. We're going to integrate that to get the integrated rate law. For zero order kinetics, it's the concentration of A at a certain point of time is equal to negative KT plus the concentration of A initially. And remember to always look at the equation of a line to figure out what important pieces of data you can gather from this. Very important to see that the slope here is actually negative K, similar to first order kinetics, but the difference we see here is that what we plot for Y is different. Remember, for first order kinetics, it was the natural log of the concentration of A at specific point in times. For zero order kinetics, it's just the concentration of A at that time or at different points in time. And then you can see that X is still plotted as time. Another important thing that I didn't mention here, but to make note of, is the y-intercept. And it's shown in the figures here. So for zero order kinetics, the y-intercept is the initial concentration of A. So if you don't know that and you have this data, you can figure it out from the equation of a line. And the y-intercept for second order kinetics is 1 over the initial concentration of A. And for first order kinetics, it's natural log of the initial concentration of A. Now I realize that that's a lot of information to remember in these equations, especially if you're not integrating them yourself or doing these derivations for an assessment. And so what I will always provide for my course is this table here. And I highly suggest that when you practice your homework problems and you study these lecture notes again, that you look at this table and utilize it so that you're familiar with it and you know where to quickly find important pieces of information. There's a lot of good stuff here. I'm not a huge fan of memorization, and so that's why I want to provide this table as a tool, since there's a lot of equations to remember. So you can see here that we have zero first and second order kinetics. It provides the rate laws. In addition, it also provides the units of K. In the previous video, I showed you how you could derive the units for K for any reaction mechanism. But this is really nice to kind of see the units of K here, because those are clues. If I have these units, then I know that I have second order kinetics. It provides the integrated rate law, which allows us to see the concentration of a reactant as a function of time. And so there's lots of information we can gather. You can see even the rearranged formula for first order kinetics. It also shows you the straight line plots for each of these kinetic series and what the slope would be and what the y-intercept would be. And then finally, in my next video, I'll focus more on the half-life expression, but it provides it on this table here, so I wanted to point it out to you right now. All right, so I have that handy because we're going to work the next problem together. So this one says, this reaction was monitored as a function of time. Anytime I hear the word time, I'm thinking integrated rate law, as opposed to just the rate law alone, which didn't allow us to look at concentration of reactants as a function of time. So if we see time here, then I want you to think, I'm eventually going to use the integrated rate law. Let's look at the other clues provided in this problem. It says a plot of 1 over AB versus time. So anytime you hear that, I want you to think, okay, that's y versus x yields a straight line with a slope, and slope for us, remember, I always represent as little m. So we have a slope of a positive 0.055 inverse molar inverse seconds. Right, there's lots of clues here before we even have to read the questions and what we really need to solve for. If you look back on your chart that I just provided for you on the previous page, what type of kinetics is taking place if you have 1 over the concentration of your reactant AB versus time? That yields a straight line with a positive slope. Good, excellent. Hoping you all said second order kinetics. So second order kinetics I like to write down the rate law or the integrated rate law, since it shows me the concentration of the reactant as a function of time. And from here, just to remind ourselves, we see that Y is 1 over the concentration of the reactant. So be mindful, A was used generically in this discussion here as the reactant. Here, the reactant is AB. So 1 over AB just represents 1 over A, okay? And also it says that it's as a function of time. So the concentration, that's time, T. And the slope is positive, and we do see that here, that the slope is positive. It's a positive K, right? So this all leads to us seeing that it is second order kinetics. In addition, something to also look out for as a clue are the units. So if we know that the slope is K and we see the units are inverse molarity, inverse seconds, if you look back at the chart here, you will also notice that the units for K for second order kinetics are inverse molarity, inverse seconds. That's not true for first order and zero order kinetics. So as you read through any of these word problems, especially with kinetics, pick up on all of these clues to help you solve the problems faster. All right, so the first question is asking us for the value of the rate constant for this reaction. K is equal to 0.055 inverse molar inverse seconds. Always use the units for K since they're different for every reaction mechanism. Write the rate law for the reaction. It's not asking for the integrated rate law. It's asking for the rate law, which is the concentration of the reactant as a function of the, and how it affects the rate of reaction. So for second order kinetics, it'd be rate is equal to K, but we already know what K is, so we'll write that in to our rate law. As long as we're running it at the same temperature, it should stay the same, times the concentration of the reactant AB, and it is second order kinetics, which we derived from analyzing the clues and the data provided at the beginning. All right. What is the half-life when the initial concentration is 0.55 molar? Now I will cover half-life in my next video, but since we're working this problem together, I will show you how to work it. So whenever you want to calculate half-life, you want to look up the correct formula. And since it's second order kinetics, if we go back to this page here, we see that the half-life is equal to 1 over K times the initial concentration of the reactant. So I'm going to write that formula down. So 1 over the rate constant times the initial concentration of the reactant. And so that is 1 over 0.055 times the concentration initially, which was 0.55. And I get that to be 33 seconds. Now be careful with the units for half-life. Most of the time we are working in seconds, but always double check with your units for the time that you use to figure out the data. You can figure that out from the rate constant unit, so it looks like we're working in seconds here. But in the next video, I will cover half-life, and we will work a problem where the time is in years, because we're looking at radioactive carbon dating, which is very slow. It has very long half-lives. All right, so let's work the last question here together. It's asking us if the initial concentration, so just pretend like we're running the same reaction, but we're changing some conditions. So now the initial concentration is 0.25 molar, and the reaction mixture initially contains no products. What are the concentrations of A and B after 25 seconds? So we already know that it's second order kinetics, and anytime it's asking me to solve for what's the concentration after some time has elapsed, then I know I must use the integrated rate law, because that allows me to see the function of concentration as a function of time. So I write that down. We already know what K is. K is always the same as long as we're working at the same temperatures here. And what I can solve for, I know it's asking for the products, A and B, but remember integrated rate law focuses on the reactants. So I'm going to focus on solving how much of this particular reactant was consumed, and then I'm going to use stoichiometry, knowing how much was consumed, to figure out how much of A and B were produced after the consumption of my reactant. Okay, so I'm going to start plugging in the data that we do know. So 1 over the concentration of my reactant at a specific point in time is equal to 0.055 inverse molar inverse seconds times, looking at 75 seconds here, that's the time interval provided, plus 1 over the concentration initially, which was 0.250 molar. And after I solve for the concentration of my reactant at 75 seconds, that is equal to 0.1230769 molar. And this is the concentration that's left over. It hasn't been consumed, right? Because remember, the integrated rate law tells us the concentration of our reactant after a specific amount of time has passed. So the concentration of my reactant at 75 seconds is 0.123 molar. Now, I need to know how much is consumed, because what is consumed must be converted into products. And I can use stoichiometry to help me solve for the concentration of products at 75 seconds. So in order to determine how much is consumed, I'm going to subtract what is left over from what I put into my beaker. So I put into my beaker 0.25 molar of the reactant. However, 0.123, remember I like to keep lots of sig figs so I don't have rounding error, that's what was left over. So 0.1269231 molar of my reactant is consumed. So this concentration is consumed. Now, based on the stoichiometry, everything is 1 to 1 to 1. And so if this was consumed, then the same amount of concentration was created for both species. And you could use the mole to mole ratio to kind of further elucidate that point. So 1 mole of the concentration, or 1 mole of A over 1 mole of AB would give you 0.127 molar of A after 75 seconds. So that's how much is produced. And since B is also 1 to 1, you would also have 0.127 molar of product B also produced after 75 seconds of reaction time. So I'm just using stoichiometry to determine how many reactants, how much reactant was consumed, and therefore I can figure out how much product was produced at that specific point in time. Alright, so I hope this video helped you to understand how useful the integrated rate law is in determining the concentration of reactants as a function of time, and how we can use the rate law to not only determine how much of reactant is left over at a specific point in time, but as well as predict how much product was produced at that point. Thank you all for watching, and see you next time.